There is a place at the bottom of the world where the wind does not whisper, it screams. Where the cold is not a season, but a permanent condition, a geological fact as solid as the bedrock buried beneath 2 miles of ancient ice. Antarctica, the largest desert on Earth, a continent-sized silence. Nothing moves here except the wind and the slow, imperceptible crawl of glaciers older than human civilization, older than recorded memory, older than almost everything we have ever touched or named or tried to understand. From above, it looks like the end of the world, white in every direction. A blankness so total it seems less like a landscape and more like an absence, as if the planet simply ran out of ideas here and left the canvas empty. No trees, no rivers visible beneath the surface, no birdsong, no warmth. The average temperature hovers around negative 57 degrees Celsius in the interior, cold enough to freeze exposed skin in seconds, cold enough to make the air itself feel dangerous. This is the most hostile terrain on Earth, and it has been this way for so long that we have come to treat its frozen identity as permanent, inevitable, eternal. But then someone starts drilling. Not metaphorically, literally. Scientists lower steel drill cores into the ice sheet and pull up cylinders of compressed time. Layers of ancient air, trapped dust. And sometimes, embedded in the sediment far below the ice, something that stops everyone in the room. A leaf, not fossilized rock that vaguely resembles a leaf. An actual structurally preserved leaf from a broadleaf tree, its veins still visible, its form still coherent after tens of millions of years of burial. Pollen grains from flowering plants, root structures, fragments of wood with growth rings, which only form in trees that experience seasonal change, trees that grew in soil, under sunlight, in warmth. There is more. There are bones. Dinosaur bones, pulled from the rocks of Antarctica's exposed coastal regions and mountain ranges. Places where the ice retreats just enough to reveal what lies beneath. Ankylosaurs, hypsilophodonts, mosasaurs in the ancient seabeds, and perhaps most remarkably a sauropod, a long-necked giant, whose remains suggest that even the very largest animals of the Mesozoic era found their way here. Not as visitors, as residents. This was their world. They were born here, lived here, and died here on a continent that, at the time, was not a frozen wasteland, but something almost unimaginable by the standards of the world we know. This is the central paradox that science has spent decades trying to fully reckon with. Antarctica, the coldest place on Earth, the continent that holds 90% of our planet's fresh water locked in ice, the landmass that has come to symbolize isolation and desolation, was once warm, green, humid, teeming with life, not just life in the sparse, scrubby way that organisms cling to hostile margins, but rich, dense, layered life. Forest life. The kind of biological abundance we associate with the tropics, not the poles. The Earth, it turns out, has more than one identity, and it is not shy about abandoning one for another. What we call Antarctica is not simply a place, it is a phase. A chapter in a story that began long before ice was even possible here. A story written in continental rock and shifting atmospheric chemistry, and the slow, grinding rearrangement of land masses across hundreds of millions of years. The frozen continent we study today is, in geological terms, a recent invention, a temporary configuration, and buried inside it, perfectly preserved like a message written in stone and pollen and bone, is the record of everything it used to be. This is what makes Antarctica unlike any other place on Earth. Every continent holds history in its rocks, but Antarctica holds a transformation so extreme, so complete, that it forces us to rethink the entire concept of planetary identity. If this place, this particular frozen silence, was once a rainforest, then nothing about Earth's present geography can be taken as fixed. The Amazon could become a desert. The Sahara could bloom again. The poles could warm. The tropics could freeze. These are not science fiction scenarios. They are things that have already happened on timescales that dwarf human civilization, but are trivial by the measure of geological time. To understand Antarctica is to understand that the planet we live on is not a stable backdrop to human history. It is a dynamic, restless system in constant negotiation with itself. With its atmosphere, its oceans, its orbital position, its own internal heat. And the story of Antarctica's ancient rainforest is one of the most dramatic demonstrations of that truth that the fossil record has ever produced. The questions this raises are not simple ones. What kind of atmospheric conditions could warm a polar continent enough to sustain a forest? How did plants grow in complete polar darkness for months at a time? What did it feel like? Ecologically, biologically, to be an animal living at the South Pole when the South Pole was green? How did an entire thriving ecosystem, one that had persisted for millions of years, collapse into the frozen silence we see today? These questions take us deep into the mechanics of ancient Earth, into plate tectonics and greenhouse gases, into orbital cycles and ocean currents, into the strange biology of darkness-adapted forests and the even stranger biology of the creatures that lived within them. But before any of that, before the explanations and the mechanisms and the science, there is an image worth sitting with. A single, almost impossible image that contains the full weight of this story's strangeness. Picture Antarctica as it was. Not white, not silent. Green canopy stretching across coastal plains. The sound of water moving, the smell of wet earth. Enormous animals moving through undergrowth that drips with moisture. And above it all, no sun. A sky locked in months of unbroken polar night. Darkness pressing down on a living forest, on warm-blooded and cold-blooded creatures alike, on a world that had no business existing and yet, undeniably, did. That forest was real. Those animals were real. And somewhere beneath the ice they are still there. To understand what Antarctica once was, you must first understand how long ago that world existed, and what it means to speak of time at that scale. The Mesozoic era began roughly 252 million years ago. It ended 66 million years ago. That span alone, 186 million years, is longer than the entire history of flowers, longer than the age of the Atlantic Ocean, longer than anything that human intuition can genuinely hold. We say these numbers, but we do not feel them, not really. They are too large for the neural architecture of a species that measures life in decades. But the rocks feel them, the fossils feel them. And if we want to understand the world that once existed at the bottom of the earth, we have no choice but to step into that vastness and let our assumptions dissolve. The planet that existed during the Mesozoic was not simply an older version of the planet we know. It was a different planet. The land masses were arranged differently. The oceans circulated differently. The atmosphere had a different chemical composition. Even the distribution of heat across the globe followed patterns that would be unrecognizable to a modern climatologist, calibrated to the rhythms of our current world. This was not Earth in a slightly altered state. This was Earth operating under an entirely different set of rules, rules that were internally consistent and stable for millions of years at a time, but rules that bear almost no resemblance to the ones governing the climate system we inhabit today. The first difference to grasp is the most fundamental. The continents were not where they are now. 200 million years ago, during the early Mesozoic, the southern half of the world's landmass existed as a single vast supercontinent called Gondwana. It was one of the largest coherent landmasses Earth has ever produced, a colossal assemblage that combined what would eventually become Antarctica, South America, Africa, India, and Australia into a single connected whole. These were not separate places with separate ecologies and separate evolutionary histories. They were one territory, one unbroken landmass stretching across the southern hemisphere, with coastlines, interior plains, river systems, and mountain ranges that flowed continuously from what is now the tip of South America all the way to what is now eastern Australia. Life moved freely across it. Plant species colonized it end to end. Animals evolved on one edge and migrated to the other. Gondwana was not a collection of future continents. It was a living system, and Antarctica was not its icy outpost. It was its heart. Over tens of millions of years, Gondwana fractured. The same internal forces that have rearranged every landmass in Earth's history, the slow convective churning of the mantle, the movement of tectonic plates driven by heat from the planet's core, began pulling Gondwana apart along geological fault lines. Africa separated first, drifting northward. Then India, breaking free and beginning its long journey toward Asia. Then Australia, gradually peeling away and moving toward the equator. South America was the last to release its grip, and when it finally did, it left Antarctica alone, isolated, surrounded by open ocean. And as that isolation deepened, something about the Southern Ocean's circulation changed in ways that would eventually prove catastrophic for everything living on the continent. But that ending comes later. During the Mesozoic, while Gondwana was still intact or only partially broken, Antarctica was connected, accessible, and warm. Connected to what? To an entire planetary climate system that operated under conditions so different from our own that they demand their own vocabulary. No ice anywhere. Not at the North Pole. Not at the South Pole. Not on the peaks of ancient mountain ranges. Not floating in the polar oceans. During the peak warmth of the Cretaceous period, roughly 145 to 66 million years ago, the Earth was almost entirely ice-free. The polar regions were cold by the standards of the tropics, certainly, but they were not frozen. They were not locked beneath glaciers or buried under ice sheets. The water that now sits in solid form at the poles was, during the Cretaceous, liquid. It was in the oceans, which ran higher than they do today by as much as 80 to 90 meters in some estimates, high enough to have swallowed the coastlines of every modern continent, high enough to flood interiors that are now dry land, high enough to turn North America into two separate landmasses, divided by a shallow inland sea. This was not an anomaly. It was not a brief warm spike in an otherwise cold history. The ice-free greenhouse state was the dominant condition of the Mesozoic. Ice caps, by the measure of Earth's full history, are the anomaly. We happen to live in one of the relatively rare periods when polar ice exists at all. Our intuition about what a planet looks like, poles white, tropics green, ice sheets stable and permanent, is an intuition built from the experience of a world that is, geologically speaking, unusually cold. The mechanism behind this warmth was carbon dioxide. During the Cretaceous, atmospheric CO2 concentrations were dramatically higher than they are today. Current levels sit at around 420 parts per million, already elevated well above the pre-industrial baseline. During the Cretaceous, estimates based on isotope analysis and geochemical modeling suggest CO2 levels range from roughly 800 to 2,000 parts per million, between 2 and 6 times higher than what we currently measure, and potentially higher still during certain periods. This was not pollution in any meaningful sense. It was the natural output of a planet with significantly more volcanic activity, less biological carbon sequestration, and no large ice sheets to lock carbon cycles into their modern configuration. The Cretaceous atmosphere was richer in greenhouse gases than anything our instrumentation has ever directly measured, and the result was a global temperature profile that would be unrecognizable to any modern organism calibrated to today's climate. Global average surface temperatures during peak Cretaceous warmth were estimated to be 8 to 14 degrees Celsius, higher than today's average. That difference, expressed at the poles, was even more dramatic. The Arctic Ocean, based on fossil evidence from marine sediments and ancient plant communities, maintained surface temperatures of around 20 degrees Celsius in summer. The Antarctic coast was similarly warm, perhaps not tropical in the sense of equatorial heat, but temperate in a rich, productive sense. Warm enough for trees, warm enough for complex ecosystems, warm enough for large animals to survive, reproduce, and evolve across millions of generations. The greenhouse effect in this context was not a crisis. It was the foundational operating condition of a planet that had been warmer than today for the vast majority of its existence. What we call normal is, from Earth's perspective, an outlier. The Mesozoic greenhouse was the baseline. And within that baseline, a continent sitting at the South Pole was not automatically condemned to cold. But warmth alone does not build a rainforest, and this is where the Cretaceous world confronts us with its deepest strangeness. Even in a warmer Earth, even with no ice at the poles, even with a greenhouse atmosphere blanketing the planet in heat, the geometry of Earth's rotation remained unchanged. The poles still tilted away from the sun for half the year. The southern extreme of the planet still experienced polar night. Not the mild dimming that high-latitude temperate regions experience in winter, but true polar darkness, weeks then months of complete absence of sunlight. Not shortened days, no days at all. And yet the forests were there. Fossil pollen retrieved from Antarctic sediments dating to the Cretaceous reveals an ecosystem dominated by conifer forests. Dense, productive tree communities more closely related to modern-day southern beaches and podocarps than anything currently found at high latitudes. These were not sparse, stunted trees clinging to marginal existence. They had growth rings indicating substantial annual growth. They had deep root systems indicating stable soils. They had associated plant communities, ferns, flowering plants, mosses, indicating layered, complex forest ecology. This was not a landscape hovering at the biological edge. It was a functioning, productive forest system that somehow managed months of complete darkness and then recovered, season after season, for millions of years. How? The answer is not simple, and scientists are still refining their understanding of it. Part of the answer lies in the biology of high-latitude plants, which evolved metabolic strategies for surviving darkness that differ fundamentally from the strategies of tropical species. Part of the answer lies in the warmth itself. Temperatures high enough that even without sunlight, biological processes could continue at reduced but functional rates. Part of the answer may lie in the structure of the Cretaceous atmosphere, which retained heat so effectively that seasonal temperature swings at the poles were far less extreme than they are today, giving organisms a gentler annual rhythm to navigate. But none of these partial answers fully dissolve the mystery. The polar darkness problem remains one of the most fascinating and unresolved questions in Mesozoic paleoclimatology, because what lives in a forest that spends months in complete darkness? What does an ecosystem do when photosynthesis becomes impossible? How do animals that depend on plant energy chains survive an energy system that seasonally shuts down? These questions lead somewhere important. Because the Cretaceous world was not just warmer than today, it was organized around a set of ecological relationships and biological adaptations that we have no living equivalent for. The organisms that inhabited Antarctic forests were not simply modern creatures transplanted into an ancient warm climate. They were products of an entirely different Earth, shaped by pressures and rhythms that no longer exist anywhere on the planet. The greenhouse conditions that made Antarctica's forests possible were not static. They fluctuated. They rose and fell across the Cretaceous, driven by volcanic pulses and ocean chemistry changes and biological feedbacks that interacted in ways we are still mapping. The climate engine of the Mesozoic was powerful, but it was not simple. And buried within its complexity were the seeds of everything that came after. The cooling, the isolation, the freezing, the silence. Something about the way Earth regulates its own heat was fundamentally different then. And understanding that difference is the only way to understand how a forest full of dinosaurs could look up at a sky that offered no sun and somehow keep living anyway. Close your eyes for a moment and try to unmake everything you know about Antarctica. Strip away the ice, pull back the glaciers, let the bedrock breathe. Now feed warmth into the system. Not tropical violence, not equatorial heat hammering down without mercy, but a deep, persistent greenhouse warmth that soaks into the soil and holds there through seasons that swing but never freeze. Add rain. Add time. Add millions of years of biological pressure selecting for organisms that can live here, thrive here, fill every available niche in a landscape that has no modern equivalent anywhere on Earth. What you are left with is not a place that exists today, but it existed. And the fossils prove it with the specificity that makes reconstruction not just possible, but unavoidable. The Antarctic rainforest of the Cretaceous period was not a single biome frozen in one configuration. It shifted over millions of years, responding to climate fluctuations and seasonal rhythms in the slow migration of the continent itself. But at its peak, during the mid-Cretaceous warmth, somewhere between 90 and 100 million years ago, it was one of the most productive and ecologically complex high-latitude environments the planet has ever produced. The coastlines and river deltas of what is now the Antarctic Peninsula, then a warm, wet landmass connected to South America, supported dense forest canopy rising high above a layered understory of ferns, mosses, and early flowering plants. The ground was soft, wet, threaded with root systems reaching down into dark, rich soil built from millions of years of accumulated organic matter. The air would have been humid, heavy with the smell of decomposing vegetation and living growth, of standing water in low-lying areas where river systems slowed and spread into swamps. This was not a tentative, fragile forest clinging to the edge of viability. It was a system in full expression, confident in its own persistence. The dominant trees were conifers, not the familiar pines of modern temperate forests, but ancient relatives more closely related to living podocarp species, a family still found today in New Zealand, South America, and parts of Africa. They grew tall. Their canopies closed overhead in ways that created genuine forest interior, shadowed and layered, with distinct zones of light and ecology from the forest floor to the upper canopy. Alongside them grew early ancestors of the southern beach, Nothofagus relatives whose descendants still populate the southern tips of South America and the subantarctic islands. These were not tropical giants, but they were substantial, and they formed the structural backbone of the entire ecosystem. Beneath them, tree ferns competed for filtered light, some growing to heights that would surprise anyone who has only seen ferns as ground-level plants. And threading through all of it, in the warmer and wetter lowland zones, were the earliest flowering plants, angiosperms that had only recently evolved and were still in the process of radiating into the ecological roles that their descendants now dominate everywhere on Earth. What made these trees remarkable was not their species identity, however. It was their growth rings. In a tropical forest where temperature and rainfall remain relatively consistent year-round, many trees grow without producing clear annual rings. There is no strong seasonal signal to interrupt growth and restart it, so the wood records no clear rhythm. But the Antarctic Cretaceous trees were different. Their fossilized wood preserves distinct rings, wide rings indicating vigorous summer growth, narrow rings indicating reduced winter activity, a pattern that tells a very specific story about the annual cycle these organisms navigated. They grew hard during the long days of the polar summer, when sunlight was available for an extended but temporary window, and then they slowed, pulled inward metabolically, and waited. Not in the full dormancy of a cold climate tree facing lethal frost, but in something more nuanced. A managed reduction of biological activity calibrated to an environment that was not cold enough to kill, but dark enough to halt photosynthesis entirely. This is one of the most fascinating biological puzzles the Antarctic fossil record presents. Trees can survive darkness through dormancy. They store energy, shut down their growing systems, and exist in a kind of suspended biological patience until light returns. But sustaining an entire complex forest ecosystem through months of polar night requires more than individual tree survival. It requires that the whole web of relationships, predators, prey, decomposers, pollinators, seed dispersers, maintain enough coherence to reassemble when conditions improve. And that means the animals had to survive too. 6 months of night. That is not a metaphor or an approximation. At sufficiently high latitudes during the Cretaceous, the polar darkness would have been absolute for significant portions of the year. Not dim, not gray. Dark. And into that darkness every autumn, the Antarctic forest descended with all its inhabitants still inside. Among those inhabitants were dinosaurs. The evidence is unambiguous on this point, even if the details remain subjects of active research and ongoing debate. Dinosaur fossils from Antarctica and from high-latitude sites in Alaska, Australia, and other Cretaceous polar regions confirm that these animals were not migrants who visited briefly during summer and retreated to warmer latitudes before darkness arrived. They were year-round residents. Their bones are found in sediments that represent the full annual cycle. They were present during winter, which means they survived it. The Antarctic dinosaur fauna, based on what has been recovered so far, was not dominated by the massive sauropods or giant theropods that tend to capture popular imagination. The polar forest was home to smaller, faster, more ecologically flexible forms. Small theropods, bipedal, likely feathered, occupying the predatory niches that smaller carnivores fill in modern ecosystems, appear to have been common. Early birds, only recently diverged from their dinosaurian ancestors, were also present, their fossils revealing a lineage that had already diversified enough to exploit the specific opportunities of a forested, seasonal, high-latitude environment. Ornithopods, the bipedal herbivores that were among the most successful plant eaters of the Cretaceous, left traces here as well, and their presence implies a herbivore community capable of processing the tough, seasonally reduced vegetation that the polar forest offered. How all of them survived the darkness is the question that no single answer has yet fully resolved. One hypothesis is migration. If some Antarctic dinosaurs were capable of traveling long distances, they could have followed the retreating light northward along what were then continuous landmasses, moving to lower latitudes where daylight persisted through the winter months, and then returning south as spring advanced. This is a biologically plausible strategy. Modern birds do something functionally similar on a global scale, and it would explain the presence of large-bodied forms that seem metabolically unlikely to have endured months without adequate food energy. But the smaller residents, the ones whose fossils appear in contexts suggesting year-round habitation, were either not migrating or not capable of migrations long enough to matter. They stayed, and staying required something more intrinsic. The deeper explanation involves metabolism, and this is where the Antarctic fossil record intersects with one of the most significant and still contested debates in all of dinosaur paleontology. Were dinosaurs warm-blooded? The traditional view inherited from decades of early paleontological thinking held that dinosaurs were ectotherms, cold-blooded like modern reptiles dependent on external heat sources to maintain their body temperature and biological function. If that model were accurate, polar dinosaurs would have been physiologically impossible. A cold-blooded animal cannot regulate its body temperature from within, cannot generate its own heat, cannot sustain metabolic activity at rates sufficient for an active predatory or herbivorous lifestyle in a cold, dark polar winter. But the evidence that has accumulated over the past 3 decades suggests a very different picture. Bone microstructure analysis, examining the internal architecture of fossilized dinosaur bones at the microscopic level, reveals growth patterns more closely resembling those of warm-blooded mammals and birds than those of cold-blooded reptiles. Fibrolamellar bone, which indicates rapid, sustained growth fueled by high metabolic rates, appears consistently across multiple dinosaur lineages. The insulating structures that appear to have been feathers, confirmed in a growing number of species, are difficult to explain in an ectotherm that does not need to retain body heat. And the very fact that small theropods survived Antarctic winters points toward endothermy as the parsimonious explanation. An animal generating its own body heat through internal metabolic processes can sustain function in cold and darkness in ways that an ectotherm simply cannot. The current scientific consensus has shifted substantially toward a view of dinosaurs as metabolically complex organisms. Not purely warm-blooded in the exact sense of modern mammals, perhaps, but occupying a physiological space somewhere between cold-blooded reptiles and fully endothermic birds and mammals. Mesotherms, in the terminology some researchers prefer. Animals capable of generating significant internal heat, sustaining elevated activity levels, and tolerating temperature variation better than a crocodile, but perhaps with less continuous metabolic demand than a wolf. For polar survival, this would have been sufficient. Not comfortable, perhaps. Not easy, but sufficient. And sufficiency, in evolutionary terms, is everything. The Antarctic forest was not an eternal summer. This point deserves emphasis because the temptation when imagining a warm, green, dinosaur-inhabited Antarctica is to render it as uniformly lush and bright. A Cretaceous Eden in permanent golden light. The reality was stranger and harder. The seasons were extreme even if the temperatures were not lethal. Summer brought continuous daylight, and the forest responded with explosive growth. Animals feeding heavily, biological systems running at full capacity. But autumn arrived with the same inevitability it always does at high latitudes. And when it came, the light retreated fast. The forest shifted register. Activity levels dropped. Whatever biological clocks governed the metabolism and behavior of Antarctic animals would have driven them toward whatever survival strategy served them. Food storage, metabolic depression, behavioral shifts, perhaps huddling in forest margins where the thick canopy reduced temperature fluctuation. It was a world organized around extremes, not the comfortable, predictable rhythms of a temperate ecosystem, but a more demanding annual cycle that selected hard for the traits that allowed survival across its full range. The animals that lived here were not random samples of the global Cretaceous fauna that happened to wander south. They were specialists, products of selection pressures that no other environment on Earth was imposing in quite the same way. That specialization would matter, because the world that shaped these animals was already, imperceptibly, beginning to change. The warmth that made everything possible was not a guaranteed permanent condition. The greenhouse atmosphere that held Antarctica above freezing, the tectonic connections that allowed ecological exchange with warmer land masses, the ocean circulation patterns that distributed heat toward the poles, these were not fixed variables in a stable equation. They were dynamic elements of a planetary system in slow, continuous motion. The forest endured, the animals adapted, but this world would not last. The Earth does not have a climate. It has a climate system, and the distinction matters more than it might initially appear. A climate is a condition. A system is a process. A condition can be described, mapped, and assumed to persist. A process must be understood in terms of its moving parts, its feedback relationships, its inputs and outputs, and crucially, its failure modes. When we look at the Cretaceous greenhouse world, at the warmth that held Antarctica above freezing, that kept polar forests growing, that sustained dinosaurs through months of darkness, we are not looking at a stable condition that simply existed for millions of years through some geological good fortune. We are looking at a system, a planetary scale machine of extraordinary complexity, running on interconnected drivers that reinforced each other in ways that kept the whole apparatus operating within a narrow band of conditions for far longer than any human institution has ever survived. Understanding that machine is the only way to understand how the Antarctic forest was possible, and understanding how it worked, how its components interacted, how its feedback loop sustained warmth across geological time, is also the only way to understand how it eventually stopped. Begin with the ocean. The modern ocean does not simply sit beneath the atmosphere as a passive body of water, it circulates. It moves in patterns driven by differences in temperature and salinity. creating a system of deep currents that transport heat from the tropics toward the poles and cold water from the depths toward the surface in ways that fundamentally shape the temperature of every landmass on Earth. The Gulf Stream, which keeps northwestern Europe dramatically warmer than its latitude would otherwise allow, is one visible expression of this system. But the full circulation pattern, what oceanographers call the thermohaline circulation, is a global phenomenon, a slow-moving conveyor belt of water that links every ocean basin and operates on timescales of hundreds to thousands of years. During the Cretaceous, this circulation system operated differently. The arrangement of continents was different, which meant the geometry of ocean basins was different, which meant the pathways along which water could move were different. Critically, the absence of polar ice sheets removed one of the most powerful drivers of modern ocean circulation. The formation of cold, dense, salty water at the poles that sinks and drives deep water circulation in today's oceans. In a world without polar ice, the ocean's thermal gradient between equator and poles was less steep, and the circulation patterns that resulted were less vigorous in some ways, but more effective at distributing warmth broadly across high latitudes. Heat generated at the tropics moved poleward not just through the atmosphere, but through ocean currents that penetrated into the high southern latitudes, delivering thermal energy to the waters surrounding Antarctica and moderating the continental temperatures that made forest life possible. The ocean was not merely a heat transport system, however. It was also a carbon reservoir, one of the largest on the planet, capable of absorbing or releasing carbon dioxide at rates that directly influenced atmospheric greenhouse gas concentrations. The relationship between ocean chemistry and atmospheric CO2 is one of the most important and most complex in Earth's climate system. Cold water absorbs more CO2 than warm water. Ice formation and melting affect ocean salinity and pH. Biological productivity in the ocean, the growth and death of marine organisms that incorporate carbon into their shells and bodies, draws carbon out of the atmosphere and eventually buries it in seafloor sediments when those organisms die and sink. In the Cretaceous, with warmer oceans and different circulation patterns, these carbon exchanges operated under different conditions, contributing to an equilibrium in which atmospheric CO2 remained elevated not through continuous volcanic input alone, but through a web of reinforcing processes that kept carbon cycling in ways that favored the greenhouse state. And then there were the volcanoes. Volcanic activity has been a continuous feature of Earth's history since the planet formed, but its intensity has varied enormously across geological time, and those variations have left fingerprints in the climate record that are unmistakable once you know how to read them. During the Cretaceous, and especially during certain intervals within it, volcanic activity was exceptionally intense. The formation of large igneous provinces, vast regions where enormous volumes of molten rock reach the surface through processes distinct from the volcanic activity at tectonic plate boundaries, release staggering quantities of CO2 into the atmosphere over geologically brief periods. The Ontong Java Plateau, a massive underwater volcanic formation in the Pacific, represents one of the largest eruptive events in the last 200 million years, and its formation during the early Cretaceous is associated with a detectable pulse of atmospheric warming. Other large igneous provinces contributed similar signals at other points in the period, each adding CO2 to a system that was already running hot. This volcanic carbon input was not offset by equivalent sequestration during the Cretaceous. The processes that draw carbon out of the atmosphere over geological time, primarily the weathering of silicate rocks, which chemically combines CO2 with minerals and eventually deposits it in the ocean as carbonate sediment, could not keep pace with the volcanic output. The result was an atmospheric carbon concentration that remained elevated for millions of years. Not because the planet was broken, but because the balance of inputs and outputs had settled into a new equilibrium at a higher level. The greenhouse state was not an accident. It was a solution. The climate system's answer to the particular combination of tectonic configuration, volcanic activity, and ocean chemistry that characterized the Mesozoic. What kept this equilibrium stable for so long was the very thing that makes Earth's climate system so remarkable: feedback. Feedback loops are mechanisms by which a change in one part of the system produces effects that then influence the original change, either amplifying it or dampening it. Climate systems contain both kinds. Negative feedbacks act as stabilizer. When temperatures rise, they trigger responses that cool the system back toward equilibrium. Positive feedbacks act as amplifiers. When temperatures rise, they trigger responses that cause further warming. The long-term stability of the Cretaceous greenhouse, despite the enormous volcanic perturbations it absorbed and the orbital variations it experienced, reflects the operation of stabilizing negative feedbacks operating over geological timescales. The silicate weathering cycle is the most important of these. When temperatures rise, weathering rates increase, pulling more CO2 out of the atmosphere over millions of years and gradually cooling the system. When temperatures fall, weathering slows, volcanic CO2 accumulates, and the system warms again. It is a thermostat, crude, slow, operating on timescales of millions of years, but real. Within that slow thermostat, however, positive feedbacks operated on shorter timescales and with greater intensity. The ice albedo feedback is the most dramatic example. Ice and snow reflect sunlight back into space rather than absorbing it, which means that a planet with large ice sheets is inherently cooler than a planet without them. The ice reflects away energy that would otherwise heat the surface. Conversely, a planet without ice absorbs more solar radiation, which warms the surface, which prevents ice from forming, which allows more absorption in a self-reinforcing cycle that keeps the ice-free state stable once it is established. During the Cretaceous, there was no ice to reflect sunlight away. The dark ocean surfaces and vegetated landmasses at the poles absorbed solar radiation that modern ice sheets would deflect. This alone was a substantial warming contribution, not the cause of the greenhouse, but a powerful amplifier of it, locking the warm state in place through its own logic. Water vapor feedback operated similarly. A warmer atmosphere holds more water vapor, and water vapor is itself a potent greenhouse gas. As volcanic CO2 warmed the Cretaceous climate, the atmosphere's water vapor content increased, trapping additional heat, driving further warming, holding more water vapor. A cascade that amplified the initial greenhouse signal and sustained it at levels that pure CO2 concentrations alone might not have reached. These feedbacks did not spin out of control into runaway warming because the slow geological thermostat eventually compensated. But on human timescales, or even on timescales of thousands of years, the amplification was real and substantial. The Cretaceous climate machine was therefore not simple. It was a layered system of drivers operating at different speeds, feedbacks reinforcing each other across different timescales, equilibrium maintained not through rigidity but through dynamic balance. The ocean moved heat. Volcanoes added carbon. Weathering slowly removed it. Ice was absent, so absorption was high. Water vapor amplified everything. And the result was a planet that maintained extraordinary warmth for tens of millions of years. Not because it was static, but because its moving parts happened to be configured in a mutually reinforcing arrangement that resisted disruption. This is the concept that carries the most weight when we try to understand both the ancient greenhouse world and the world we inhabit today. Not temperature, not CO2 concentration, but configuration. The particular arrangement of planetary systems and their feedback relationships that determines which stable state a climate settles into, and how resistant that state is to perturbation. The Cretaceous greenhouse was one stable configuration. The glacial world we live in, with polar ice sheets, vigorous thermohaline circulation, moderate atmospheric CO2, and a climate sensitive to orbital variations, is another. These are not points on a simple spectrum from cold to warm. They are distinct modes of planetary operation, each internally consistent, each maintained by its own web of reinforcing feedbacks, and each separated from the other by threshold conditions that, once crossed, trigger reorganization of the entire system. Those thresholds are what scientists call tipping points. They are the moments when a system that has been absorbing perturbations within its stable range instead crosses into a new configuration, from which return requires far larger forcing than the initial crossing. They exist in climate systems because of the nonlinear nature of feedback relationships. Small changes can be absorbed up to a point, but beyond that point, the feedbacks that previously stabilized the system begin to amplify the change instead of damping it. The stable state collapses, a new stable state asserts itself, and the transition between them can be geologically rapid. Not instantaneous by human standards, perhaps, but abrupt by the measure of a system that previously changed only over millions of years. The Cretaceous greenhouse eventually crossed such a threshold. Not immediately and not simply. The transition from greenhouse to icehouse Earth was a long, complex, multi-stage process involving tectonic reorganization, volcanic changes, ocean circulation shifts, and biological evolution operating in concert over tens of millions of years. But the fundamental mechanism was a crossing of a boundary beyond which the self-reinforcing feedbacks that had sustained warmth began instead to sustain cooling, and the system settled into a new configuration. Colder, drier, with growing ice sheets that reflected more sunlight, which drove further cooling, which grew more ice, which reflected more light, which drove further cooling still. What is striking when you examine the mechanics of this transition carefully is not that it happened, but that the same feedback architecture that sustained the greenhouse world for so long was ultimately implicated in its collapse. The very processes that reinforced warmth, ice albedo water vapor, ocean heat distribution, became, in a different configuration, the processes that reinforced cold. The engine did not brake, it shifted gears, and when it shifted, everything built within the warm configuration. The forests, the ecosystems, the animals adapted to polar darkness and seasonal extremes, faced a world that was increasingly hostile to their existence. The planet regulates itself, but regulation is not the same as preservation. The mechanisms that maintain planetary stability over geological time are indifferent to the particular configurations of life that arise within any given stable state. They operate at scales so vast and with such geological patience that entire evolutionary lineages can rise, flourish and vanish within the margin of a single feedback cycle. But engines can stall, and when they do, the silence they leave behind is absolute. Nothing in geology announces itself. There are no warning signs posted at the margins of tectonic plates. No atmospheric alarms triggered when carbon concentrations begin their long decline. No moment at which the living things occupying a warming or cooling landscape receive any signal that the world they were born into is becoming incrementally and irreversibly a world that will no longer accommodate them. Change at geological scale is change without drama, at least from the inside. What feels in the fossil record like a slow and inevitable transformation was experienced, if it was experienced at all, as simply the texture of ordinary existence. Seasons that seemed slightly harder, winters that seemed slightly longer, forests that seemed over generations no individual organism could bridge, slightly thinner than they used to be. This is how Antarctica lost its warmth. Not in a single event, not in a catastrophe that announced itself with the clarity of a mass extinction, but in a process so gradual, so distributed across time, that its full arc can only be perceived by something that can read the rock record across tens of millions of years and hold the entire sequence in mind simultaneously. We are the first species capable of doing that, and what we see when we read it is a story of loss on a scale that has no parallel in any human narrative tradition. It began with movement. The fragmentation of Gondwana, which had been ongoing since the early Mesozoic, reached its decisive phase during the late Cretaceous and into the Paleogene, the period following the Great Extinction at the end of the Cretaceous 66 million years ago. Australia, which had been the last significant landmass maintaining a connection to Antarctica along its northern margin, continued its drift northward. The separation was not sudden. It proceeded at rates measured in centimeters per year, the speed at which fingernails grow, the speed at which continents move when driven by the slow convective churning of the mantle beneath them. But centimeters per year, sustained across millions of years, accumulate into thousands of kilometers of open ocean. And open ocean, in the context of atmospheric and climate dynamics, is not merely empty water. It is a boundary, a thermal and circulatory reorganization of the entire southern hemisphere. South America held on longest. The connection between Antarctica and the southern tip of South America, through what is now the Scotia Arc and the islands scattered across the Southern Ocean, persisted into the Eocene epoch, somewhere between 50 and 34 million years ago. Exactly when this connection finally broke has been a subject of scientific debate, with different lines of evidence suggesting different timings. But at some point during the Eocene, the last land bridge failed. The final geological thread connecting Antarctica to the rest of the world's land masses snapped. And in the water between the separated continents, a gap opened that would become one of the most consequential geographical features in Earth's climatic history. The Drake Passage. By any ordinary measure, the Drake Passage is simply a stretch of ocean, the body of water lying between the southern tip of South America and the Antarctic Peninsula, roughly 800 kilometers wide at its narrowest point. Notoriously violent in its weather and seas, a passage that sailors have feared for as long as humans have navigated the Southern Ocean. But its significance is not navigational. It is climatic, because the opening of the Drake Passage removed the last barrier to something that had not existed anywhere in the Southern Ocean for tens of millions of years. A completely unobstructed circumpolar water pathway. Water, like all fluids, follows the path of least resistance. In the Southern Ocean, the dominant wind pattern drives surface water relentlessly eastward, circling the Antarctic continent in a pattern that is ultimately determined by the Coriolis effect and the prevailing westerlies. Before the Drake Passage opened, this eastward drive was blocked. Water circulated, but it was forced northward when it encountered land, mixing with warmer subtropical water masses, losing its cold character, redistributing thermal energy in ways that moderated Antarctic temperatures. The continent was cold by the standards of the tropics, but it was connected, thermally, oceanographically, biologically, to the warmer world beyond it. When the Drake Passage opened, that connection broke. The Antarctic circumpolar current established itself, slowly at first, building over millions of years as the passage widened and deepened, eventually becoming the strongest ocean current on Earth. It flows continuously eastward around Antarctica, driven by the westerly winds that dominate the high southern latitudes, and it circles the continent in an unbroken loop that has no land to interrupt it anywhere along its path. Its volume of flow dwarfs every other ocean current on the planet. It moves approximately 130 to 150 sverdrups, a unit of measurement representing 1 million cubic meters of water per second. A figure so large it requires a moment to sit with. It is not just the strongest current on Earth. It is by a significant margin the largest continuous movement of water anywhere in the ocean system, and its effect on Antarctic climate was thermal amputation. By circling the continent in an unbroken band, the Antarctic circumpolar current effectively isolated Antarctica from the warmer water masses of the subtropical and tropical ocean. The warm currents that had previously penetrated toward the continent's coastlines, moderating temperatures and delivering oceanic heat to the southern landmass, could no longer reach it. They were deflected northward and eastward by the circumpolar current, redirected away from the continent before they could deliver their thermal energy. Antarctica, for the first time in its geological history, was truly alone, surrounded by a wall of cold, circulating water that insulated it from the warmth of the rest of the planet. Not protecting it from cold, but protecting the cold from warmth. The continent was sealed inside a thermal prison of its own oceanographic making. The cooling that followed was not instantaneous. Feedback systems that had maintained Antarctic warmth for tens of millions of years do not collapse in a geological eye blink. The atmosphere over Antarctica remained warm enough for a time to sustain modified versions of the ecosystems that had flourished there. But the trajectory had changed. The direction of travel was now irreversible in the sense that matters most. The tectonic configuration that had allowed warmth was gone, and tectonic configurations do not reverse in the timescales relevant to any living ecosystem. Antarctica's position, its isolation, its relationship to ocean circulation, these were now fixed features of a new planetary geography that would persist for millions of years into the future. The forests felt it first. The rich Cretaceous rainforest had already been transitioning through the late Cretaceous and into the Paleogene, responding to the broader global cooling that had begun even before Antarctica's full tectonic isolation. The warm, adapted conifers and tree ferns of the deep Cretaceous had already been giving way to more cold-tolerant flora. Nothofagus, the southern beech, became increasingly dominant as temperatures moderated, its ecological flexibility allowing it to persist across a wider temperature range than the more specialized tropical elements of the earlier forest. By the Eocene, the Antarctic forest was already a different ecosystem from its Cretaceous predecessor. Cooler, more seasonal, less species-rich, but still a genuine temperate forest, covering significant portions of the continent's habitable land. Then the Drake Passage fully established its current, and the trajectory steepened. Eocene Antarctic sediments preserve a detailed record of the deterioration. Pollen profiles, the ratio of different plant species represented in sediment layers corresponding to different time periods, show a progressive shift from diverse temperate forest assemblages toward simpler, more cold-tolerant communities. Tree species that required genuine soil warmth disappeared from the record first, their absence marking the point at which winter temperatures had dropped below the threshold those species could tolerate. Ferns retreated from the upland areas where they had previously thrived, surviving longer in the coastal lowlands where maritime influence moderated the worst of the cold. Flowering plants reduced in diversity. The forest canopy thinned. There is something in that thinning that resists being rendered purely as data. A forest thinning over millions of years is not a forest dying suddenly. It is a forest forgetting, generation by generation, the ecological memory of what it used to be. Each tree that fails to reproduce at the cold margin of its range does not experience itself as part of a collapse. It is simply a tree that did not thrive. Its absence is not noted. The forest it belonged to does not know it is contracting. But the contraction is real, and in the sediment record, it is written with the clarity of an obituary composed from pollen grains. By the late Eocene, somewhere around 34 million years ago, the threshold was crossed. The precise timing remains a subject of ongoing research, and the event, called the Eocene-Oligocene transition, was likely not a single moment but a rapid deterioration by geological standards, perhaps spanning a few 100,000 years. But its signature in the rock record is unmistakable. A major glaciation event that placed large permanent ice sheets on Antarctica for the first time in tens of millions of years. The transition was abrupt enough in geological terms to have its own designation. It is sometimes called the Great Cooling, or simply the EOT, and its effects on global climate, on sea levels, on ocean circulation, and on biological diversity across the planet were profound and lasting. The ice did not come from nowhere. Snow had been falling on Antarctica throughout the cooling period, as it falls anywhere when temperatures drop sufficiently. But snow that falls in a warm climate melts in summer. The seasonal energy balance determines whether snowpack accumulates or retreats, and for millions of years through the gradual cooling, summers in Antarctica had remained warm enough, barely and then less barely, to melt what winter deposited. The ice-free state persisted, not because Antarctica was warm in an absolute sense, but because the summer energy input remained above the threshold required to clear the previous winter's accumulation. When that threshold was finally crossed, when summers became cold enough that not all the winter snowpack melted, the dynamic changed. Snow accumulated from one year to the next. As it accumulated, it compressed into glacial ice. As ice built up, the ice albedo feedback that had been irrelevant in a warm world began to operate with devastating effectiveness. Ice reflected sunlight that had previously warmed the surface, cooling the climate further, allowing more ice to form, which reflected more sunlight, which cooled further still. The feedback loop that had kept Antarctica warm through the absence of ice now operated in reverse, keeping Antarctica cold through the presence of it. What had taken millions of years to begin took relatively little time to consolidate. The ice sheets expanded. The remaining forest retreated to coastal refugia, then to isolated pockets, then to nothing. The last trees on Antarctica, if any survived into the Oligocene, as some fossil evidence tentatively suggests, would have been small, stressed, living in the marginal zones where some residual warmth from the surrounding ocean barely kept the soil above freezing. They would not have known they were the last. They would have grown as trees grow, reaching toward light, setting seed in hope of a spring that, for the lineage as a whole, was no longer coming. At some point, the last seed failed to germinate. The last root system gave up its hold on soil that was becoming permanently frozen. The last remnant of what had once been one of the most extraordinary high-latitude ecosystems in Earth's history yielded to the cold. Silence followed. Not the silence of aftermath, dramatic and temporary, but the silence of a new, permanent state. The silence of ice, of cold, so complete and so self-reinforcing that nothing with the biological complexity of a forest has disturbed it in 34 million years. The rainforest did not vanish in an instant. It retreated year by year, generation by generation, species by species, until the continent that had once been green was white. And then it was buried under ice that built, slowly and without mercy, into the 2-mile deep sheets that cover Antarctica today. The fossils lie beneath that ice still, leaves, pollen, bones, the compressed record of a world so different from the one that replaced it that finding it feels less like discovery and more like excavation of a memory the planet itself had forgotten it kept. The rainforest vanished beneath ice, but the ice preserved what the rainforest left behind. The drill goes down slowly. It has to. The ice it is penetrating took millions of years to form, layer by layer, each annual snowfall compressing the one beneath it into something denser and older and more information-rich than the season that deposited it. A single ice core, a cylinder of compressed frozen history pulled from the Antarctic ice sheet, can contain within its length a continuous climate record stretching back hundreds of thousands of years. The air bubbles trapped inside it are literal samples of ancient atmosphere, preserved in a state so intact that scientists can measure the CO2 concentration of air that no living thing has breathed since long before our species existed. Drilling into the Antarctic ice sheet is not merely an engineering exercise. It is an act of time retrieval, precise and patient, and humbling in what it reveals. But the ice cores are only one layer of what Antarctica holds. Beneath the ice, in the sediment and rock below the glacial sheet, in the exposed outcrops where the ice retreats enough to reveal the continent's bedrock, and in the coastal regions where erosion and tectonic uplift have brought ancient material to the surface, there's something older still. Something that the ice preserved not by freezing, but simply by burying, pressing down on it with 2 miles of weight, sealing it from the oxygen and biological activity that would otherwise have decomposed it across geological time, keeping it in a state of compressed preservation that has no equivalent anywhere else on Earth. A forest found under a mile of ice. Not metaphorically, not in the loose sense that geologists sometimes use when they speak of fossil-bearing strata as preserved ecosystems. Literally a forest. Its trees fossilized in place, their root systems still embedded in the ancient soil horizon. Their trunks preserved as carbonized or silicified remnants of wood that grew in sunlight tens of millions of years ago, on a continent that has since been buried under the largest ice sheet in the southern hemisphere. The discovery of in situ fossil forests in Antarctica, trees preserved not as transported fragments but as standing remnants in their original growth positions, is one of the most striking achievements of Antarctic paleontology, and its implications have reverberated through climate science in ways that are still being fully processed. The scientific investigation of Antarctica's ancient past has not been a single dramatic discovery, but a cumulative process spanning more than a century of increasingly sophisticated fieldwork. The earliest Antarctic expeditions of the early 20th century returned with geological samples that hinted at the continent's warm history. Robert Falcon Scott's ill-fated Terra Nova expedition famously recovered plant fossils from near the South Pole. Specimens found on the bodies of Scott and his team during the search party's discovery of their final camp. Those fossils, Glossopteris leaves, the same plant that had already been found in South America, Africa, India, and Australia, providing early evidence for the supercontinent Gondwana, were collected in extremis on a journey that cost 5 lives, and they arrived in scientific hands as physical objects of extraordinary significance. Proof that the coldest place on Earth had once grown plants. That beginning shaped everything that followed. Each subsequent generation of Antarctic science has built on it, refining the picture of what the continent was with tools and techniques that Scott's era could not have imagined. Sediment cores drilled from the seafloor surrounding Antarctica capture the record of glacial advance and retreat in layers of fine-grained material that settled slowly through the water column over millions of years. Each layer carrying pollen, microscopic organisms, and chemical signatures that encode the temperature, ice extent, and biological productivity of the surface waters above at the time of deposition. These cores, some of them recovering sediment from more than 30 million years ago, have allowed scientists to reconstruct not just the fact of Antarctica's ancient warmth, but its texture. The seasonal rhythms, the rate of cooling, the biological communities that persisted through each phase of the transition. The International Ocean Discovery Program, which has coordinated deep-sea drilling operations in the waters around Antarctica for decades, has produced some of the most revelatory data. Cores retrieved from the continental shelf, the shallow underwater platform extending from Antarctica's coastline, have penetrated sediments laid down during the Cretaceous and early Paleogene, recovering material that preserves the full biological richness of the ancient coastal ecosystem. Pollen from conifer species, spores from tree ferns, microscopic algae from warm, shallow coastal waters. Chemical isotope ratios in microscopic shell-bearing organisms called foraminifera that encode the temperature of the seawater in which those organisms lived. Each of these proxies, each different line of evidence pointing toward the same ancient conditions, adds resolution to a picture that has become, over the decades, remarkably detailed. What that picture shows has repeatedly surprised scientists who thought they understood the range of climate variation Earth was capable of producing. The sediment records from the Cretaceous warm period contain signatures of sea surface temperatures around Antarctica that initially seemed too high to be credible. Early analysis of certain proxy indicators suggested coastal water temperatures of 20 degrees Celsius or higher, warmer than the modern Mediterranean in summer, warmer than the modern North Sea at any time of year, at latitudes approaching the Antarctic Circle. When these results were first published, they generated significant scientific skepticism. The climate models of the time, the computational systems used to simulate Earth's climate under different atmospheric and tectonic conditions, could not reproduce temperatures that warm at those latitudes even when fed the elevated CO2 concentrations that the geological record suggested. The models kept predicting polar temperatures colder than the fossils indicated. The discrepancy was not small, It was not a rounding error. It was a systematic failure of every model to account for something the ancient Earth had actually done. This is the moment in the scientific detective narrative where the evidence refuses to behave, where the data exceeds the framework built to interpret it, where the honest response is not to adjust the data, but to interrogate the framework. The interrogation has been ongoing for more than 2 decades, and it has changed climate science in fundamental ways. The problem, as researchers gradually identified it, was not that the proxy data was wrong. Multiple independent lines of evidence from different research groups using different methods kept converging on the same uncomfortably warm temperatures. The problem was that the climate models were missing something. Some process, some feedback mechanism, some aspect of the Cretaceous climate system was operating at intensities or through pathways that the models had not adequately represented. Identifying what that missing element was has driven some of the most intensive model development work in modern paleoclimatology. Several candidates have emerged. Clouds, specifically the behavior of low-level marine clouds over polar oceans in a warm world, may have played a role that standard climate models underestimate. In a warmer climate with less temperature contrast between tropics and poles, the formation and persistence of the reflective cloud layers that currently cool high-latitude ocean surfaces may be reduced, allowing more solar radiation to reach the surface and driving additional warming. If Cretaceous polar skies had systematically fewer or thinner low clouds than modern models assume, the extra solar absorption alone could account for a significant fraction of the observed temperature anomaly. This is not a settled question. Cloud behavior remains one of the most challenging components of any climate model. But the evidence from ancient climate proxies is pushing researchers toward taking polar cloud feedbacks more seriously than they previously had. The implications of this pursuit extend far beyond academic interest in ancient climates. Climate models are not solely historical tools. They are the same computational frameworks used to project future climate change, to estimate how much warming a given increase in atmospheric CO2 will produce, to assess the sensitivity of the climate system to perturbation. If those models have been systematically underestimating the warming response of polar regions, as the Antarctic fossil record strongly suggests, then their projections for the future behavior of polar climates may share the same bias. The ancient greenhouse world of the Cretaceous is not merely a curiosity of deep time. It is a calibration dataset for the tools we use to understand our own climatic future. This is what the fossils beneath the ice are ultimately. Not just biological specimens, not just evidence of a warmer past. They are data points in a calibration exercise of existential relevance. Evidence that the Earth's climate system is capable of operating in modes that our models have historically struggled to reproduce, which means that our confidence in those models must be tempered by the humility of what the rock record keeps showing us. That humility is one of the most striking things about the scientists who work with this material. Spend time reading the literature of Antarctic paleoclimatology, and you encounter, beneath the technical language and the cautious scientific hedging, a genuine and recurring sense of astonishment. Not just at what the fossils show, but at how consistently the ancient record exceeds expectation. How regularly the data from core samples and outcrop surveys pushes beyond the envelope of what the prevailing models considered possible. How many times a research team has pulled material from the Antarctic sediment record and found evidence of conditions so different from the present that the first response before interpretation begins is simply to verify that the sample is not contaminated or misdated. A forest found under a mile of ice does that to scientific intuition. It disrupts the comfortable assumption that the world we know is the world that has to be, that its configurations are somehow more natural or more stable than the dramatically different configurations that preceded them. Antarctica is white. We know that. It has been white in the sense of being ice-covered for 34 million years. But 34 million years is not forever. It is not even particularly long, measured against the full geological history of the planet. And the evidence preserved in the ice and beneath it keeps making the same quiet argument. This is not how Antarctica has always been. This is not necessarily how it will always be. The fossils are patient. They have been waiting for precisely as long as they needed to wait. Through the ice ages that buried them, through the long stability of the current glacial configuration, through the entire span of human existence, which barely registers as a whisker on the timeline of their preservation, they waited until we developed the technology to find them, the analytical tools to read them, and the theoretical frameworks to understand what they were trying to say. What they say is this: Earth is not stable in the way we intuitively believe it to be. It is stable only within configurations, and it has inhabited many configurations across its history that would be unrecognizable from where we stand. The Antarctic forest was real. Its disappearance was real. The processes that caused it to disappear were real, measurable, and in their fundamental physics not entirely unlike the processes that concern atmospheric scientists today. The scale was different. The causes were different. The timescale was incomparably longer. But the basic architecture of the system, greenhouse gases, feedback amplification, tipping points, threshold crossings that reorganize entire planetary climate states, is the same architecture. If Antarctica changed once so completely and so irreversibly that a continent of rainforests became a continent of ice, then the question of what Earth's climate is capable of producing in the future is not a question that historical experience alone can answer. The historical experience goes back much further than we tend to look. And the further back it goes, the more dramatically it expands the range of possible futures we must be willing to consider. The fossils beneath the ice do not warn. They do not predict. They simply exist in their mute, compressed geological patience as evidence of what this planet has already done. And that, in its way, is more unsettling than any warning could be. There is a version of Earth that no living human has ever seen, and no human will ever see. And yet it was as real as the ground beneath your feet. It had weather, it had seasons, it had ecosystems of extraordinary complexity, animals of remarkable sophistication, forests that grew and died and grew again across millions of years of continuous biological inheritance. It had a south pole covered not in ice but in trees, and beneath those trees, in the wet soil of a continent that no longer exists in any form we would recognize, animals moved through darkness and emerged into light and lived out the full biological drama of existence on a planet that was, in almost every measurable sense, different from the one we inhabit. That world is gone. Not diminished, not altered, gone, replaced so completely by the world that followed it that the only evidence of its existence lies buried under 2 miles of ice, compressed into fossil leaves and ancient pollen and bones that have not felt air or light since before our genus existed. The transformation was total, The continent that hosted one of the most remarkable high-latitude ecosystems in Earth's history is now the coldest, driest, most biologically barren major landmass on the planet. The same place, an entirely different world. This is what Earth does. Not occasionally, not under exceptional circumstances requiring the intervention of asteroid impacts or catastrophic volcanism, but as a matter of ordinary geological business, conducted through the patient operation of forces that require no drama to produce consequences of staggering magnitude. Continental drift, ocean circulation shifts, carbon cycle fluctuations, feedback loops crossing threshold conditions. These are not exotic phenomena. They are the routine mechanics of a planet with a molten interior, a dynamic atmosphere, and a climate system whose stability is always conditional, always dependent on the particular configuration of components that happens to be operating at any given time. Change the configuration, and the climate changes with it. Change the climate sufficiently, and the ecosystems built within it become impossible. And the planet, indifferent to what it is losing, builds something new. Human civilization has existed entirely within one of these configurations, the climatic window that allowed agriculture to develop, that permitted the construction of cities in coastal regions and river deltas and temperate plains, that maintained sea levels and temperature ranges and precipitation patterns stable enough for complex societies to plan across generations. This window opened roughly 12,000 years ago, at the end of the last glacial maximum, and it has remained open, with relatively minor fluctuations, for the entire span of recorded human history. Every civilization we have ever built, every crop system we have ever developed, every coastline we have ever settled, every climate assumption embedded in our architecture and our agriculture and our mythology has been calibrated to this window. We did not choose it. We simply arrived during it, and we have come to treat its conditions as the natural state of the world. But the Antarctic record makes the presumption of that normalcy very difficult to maintain. Because this configuration, temperate climates, polar ice, moderate sea levels, a carbon cycle operating within the bounds of the Holocene, is not Earth's default. It is one of Earth's phases, and phases in geological time are temporary by definition. The ice ages that periodically deepened and retreated across the last 2.5 million years are themselves a relatively recent feature of Earth's history, products of a long-term cooling trend that began with Antarctica's tectonic isolation and deepened through the Cenozoic into the rhythmically glaciating world of the Pleistocene. Before that cooling trend, before the ice ages became a recurring feature of the planet's rhythm, there were extended periods of warmth that make the current interglacial feel like a brief, mild interval between much larger stories. The Cretaceous greenhouse lasted for tens of millions of years. The transition into the current icehouse state took tens of millions more. The orbital cycles that drive the advance and retreat of ice sheets operate on timescales of tens to hundreds of thousands of years. Against these rhythms, human civilization is not even a rounding error. It is a perturbation so brief that future geologists, whatever form they take, may struggle to identify it clearly in the stratigraphic record. We exist, in geological terms, at a resolution below the noise of ordinary planetary variation. And yet we are not powerless within our moment. The lesson of the Antarctic fossil record is not fatalism. It is not an argument that change is so inevitable and so vast that human choices become meaningless. The lesson is more precise and more demanding than that. It is that climate systems are sensitive to the configuration of their components, that feedback loops can amplify initial changes into transformations far larger than the original forcing, and that the planet does not automatically return to conditions favorable to any particular form of life once those conditions have been disrupted. The Antarctic forest did not return after the ice sheets formed. The tectonic configuration that isolated the continent remained in place. The circumpolar current continued to block warm water from reaching the coast. The ice albedo feedback that reinforced glaciation continued to operate with the same implacable physics that established it. The new configuration locked in and it has held for 34 million years. Stability, once lost, is not guaranteed to reassert itself on any timescale relevant to the life that depended on it. This is what the deep time record teaches, and it teaches it not through warning but through demonstration. Through the simple geological fact of a continent that was green and is now white, and has been white longer than mammals have been the dominant large animals on Earth. There is something else the Antarctic record offers, something quieter than the scientific implications and more personal than the systemic analysis. It offers perspective. The kind of perspective that is genuinely difficult to achieve from inside the compressed urgency of a human lifetime, but that the fossil record makes available to anyone willing to sit with it long enough to let its scale register. The planet has been here before, not specifically here, not with these continents in these positions and these organisms filling these niches, but in analogous states of dynamic transformation, navigating transitions between climate configurations whose endpoints could not be predicted from their starting conditions. It has produced worlds of extraordinary beauty and complexity, and then replaced them with other worlds, equally complex in their own configuration, equally temporary in their own tenure. It has done this repeatedly across timescales that reduce all of human history to a single afternoon, in a story measured in billions of days. And it will continue to do it whether or not any creature capable of recognizing the pattern exists to observe the next iteration. Antarctica is the most dramatic single demonstration of this truth that the geological record preserves. No other place on Earth contains within one location such a complete record of such a total transformation. From rainforest to ice sheet, from the warmth that sustained dinosaurs through months of polar darkness, to the cold that has made the continent essentially uninhabitable for complex terrestrial life for 34 million years. The same bedrock, the same position on the globe. An almost unrecognizable difference in everything else. Standing at the edge of the Antarctic ice sheet today, or simply holding in mind the image of it, white and silent and seemingly eternal under a pale polar sky, it is nearly impossible to feel the forest that lies beneath. The weight of ice between present and past is not just physical. It is temporal, conceptual, experiential. The forest is simply too far removed from anything the modern landscape offers as a foothold for imagination. But it is there. The leaves are there. The pollen is there. The bones are there, in the rock below the ice, in the sediment cores retrieved by patient scientists drilling down through compressed time, in the outcrops where geology has briefly exposed what the glaciers have otherwise buried. The forest is there, waiting in the way that only fossils can wait. Without urgency, without expectation, without any particular interest in whether it is found or understood or remembered. And above it, pressing down with the full weight of 34 million years of cold, the ice lies white and silent and absolute. Exactly as it does at the opening of the story. exactly as it did before we knew what it was covering. The same blankness, the same apparent emptiness, the same wind moving across a surface that looks from above like the end of the world. Beneath it, a forest. Still there, still waiting. The coldest place on Earth. Still keeping the secret of the warmth it used to be.